Hello everyone, my name is Asad Ali and you are watching Scientist Academy. So today we are going to discuss the detailed derivation of solution of Helmholtz equation under Paraxial Approximation, in which the beam is of Gaussian type, means the transverse intensity profile of the electromagnetic beam is Gaussian. So this is going to be a detailed derivation, and the video is going to be a little longer than usual. So I hope you will bear me in this regard. So I think we should better start now. So what is Gaussian beam? So Gaussian beam basically is a beam of electromagnetic radiation with high monochromaticity, whose amplitude envelope or the amplitude function in the transverse plane is given by Gaussian function, right? So for that, obviously we have to solve the wave equation from Maxwell's equation. So equation number 1 is the wave equation, where del square is the Laplacian operator in three-dimensional space x, y, and z, and c is the speed of light. So on the left side there is a Laplacian of electric field function as a function of space and time. Similarly, on the right side we have the time derivative, and of course this is a second order derivative, pardon me for that. So yeah, there is a square. Yeah, fine. So yeah, so this is the Maxwell equation, the wave equation derived from the Maxwell equation. So where we assume that electric field as a function of time and space can be written as the separable product of special solution E as a function of x, y, z, and temporal solution, which is the temporal phase e to the power minus j omega t, where j is the imaginary number with omega being the frequency of wave and time is the time variable. So if we put equation number 2 in 1 and do the derivatives on from the Laplacian side and the temporal part side, so we will come up with this equation number 3. So this is a very famous equation in physics, also called Helmholtz equation, right? And so we basically remove these temporal phases from these both terms. So this is the thing left with us. This is called Helmholtz equation, right? So now we assume that the amplitude of wave at a certain value, say x equals y equals z equals 0, means for x, y, and z equals 0, the amplitude of this electric field is E naught. Obviously, this is the electric field E naught. So now we assume that as the wave propagates, we assume the special profile of the wave being psi, the amplitude profile, function profile, or you can say the geometrical profile of the shape, geometrical profile or the shape of the envelope, wave envelope, which is psi as a function of psi x, y, z, right? As a wave propagating along z direction with the special phase e to the power minus j k z. This e to the power minus j k z is the usual special phase, or this is also called longitudinal phase of plane wave propagating in z direction. So using these two terms, psi as a function of x, y, z and e to the power minus j k z, the special part of electric field E of x, y, z can further be written as this, right? Got it? So this is the thing, and we assume that psi, which is the special profile of the wave at any value of x, y, and z, right, is the special profile. So our interest is to find what this psi is, right? So in order to do that, what we do is we plug this equation number 4 in equation number 2, which is Helmholtz equation, and perform the necessary or indicated operation. So we come up with this equation number 5, where I have not where I have put del t for the transverse Laplacian operator del t square t for transverse, which is the Laplacian operator in x and y space, whereas I basically took the derivative with respect to z space separately here, right? So this is the separate derivative with respect to z axis. So then what we do is we took this term as it is over here, and we basically place e of x y z by equation number 4. Similarly, we perform these operations, which is this derivative operation, and similarly we apply the product rule of differentiation, and when we open this equation number 5 properly, we come up with this equation number 6. Here you can see we have two terms similar but opposite, same but opposite, these things. So we can cancel these two terms from here. So if we further simplify, we come up with this equation. Del t square psi plus partial square psi by partial z square minus 2jk partial psi by partial z equals 0. Right? So this is the new form of this Helmholtz equation after assuming the special profile of electric field E of x, y, z equal to is the product of psi and longitudinal phase due to the spatial propagation of wave e to the power minus j k z. Right? So now here, in order to solve this equation, we assume that our beam is not going to change its envelope profile significantly as it propagates along z-axis. So we assume that the first derivative of psi with respect to z is greater than the second derivative of psi with respect to z. So this second order derivative term is neglected, right? This approximation is also called paraxial approximation or smaller angle approximation. This approximation can be used if we assume that our beam is propagating along z direction, right? And our wave vector k is making an angle theta with respect to z, but remember that the k is not diverging from its original path significantly because theta is small, right? So in that case, the special profile is not going to change significantly. So that is why I said partial square psi by partial z square is goes to 0. Right? So if theta is small, sometimes people used to write sinus theta is approximately equal to theta, because as you know there are higher terms as well. So if theta is small, obviously these terms scales. So finally we are left with sine theta. And since sine theta is proportional to tan theta, so we can also write it as tan theta. So this comes in the same paraxial approximation, right? So paraxial approximation says the wave vector of the wavefront is not going to diverge significantly when it propagates when the beam propagates along z-axis, right? So the spatial profile is not going to change significantly. So that is why the higher order derivatives are 0. And similarly, cos theta is obviously, as you know, 1 minus x square over 2 factorial plus x4 over 4 factorial. So is theta here. So these terms are also negligible, and so we assume theta is approximately equal to sine theta is approximately equal to tan theta, which is equivalent in saying that theta is cos theta is approximately equal to 1, right? So this is the paraxial approximation. So if we ignore this term using this paraxial approximation, our equation becomes this. This is a very simplified form. This becomes relatively simple than equation 7, right? And now we impose some geometrical consideration that we are dealing with the cylindrical symmetry. The beam is possessing cylindrical symmetry. So we can transform this Laplacian operator, transverse Laplacian operator, in the form of radial part, or you can say the cylindrical coordinates. So equation 8 turns into equation number 9. So I have not derived the thorough derivation of this Laplacian in terms of cylindrical coordinate. You can find it you can find this expression in any graduate level mathematical physics book, right, or any differential geometry book. So this is our new paraxial Helmholtz equation, right? This is the paraxial Helmholtz equation in cylindrical coordinate. So if you are interested in the relevant material regarding this lecture, then you can consult chapter 3, which is Gaussian beam in the laser electronics book by Joseph Verdian, right? So this is the book on laser electronics. So now that we have our differential equation, so the next task is to guess the solution or come up with the solution of this differential equation which satisfies this differential equation 9. So we guess the solution having the functional form like equation number 10. Psi is equal to exponential minus j into p of z. P is some unknown parameter or function of z, plus kr square divided by 2q of z, where q of z is an unknown parameter. Obviously, these two parameters are going to be of very extreme importance in understanding this Gaussian beam. For that, our next task is to specify what these are, right? So our next goal is to find, the immediate goal is to find these two parameters, which when plugged into equation 10 will satisfy equation number 9, right? So the rest of the lecture is based on this, the derivation or the function, defining the functional form of P and Q, right? So what next to do? Take your equation number 10, which is the guess solution of this differential equation, approximate paraxial equation, paraxial Helmholtz equation in cylindrical symmetry, which is equation number 9 in equation 10. So if you put and perform some differentiation or do some calculus, you come up with equation number 12, right? And now we can rearrange with certain factors to be common between different terms. So if we rearrange equation number 12, we are left with equation number 13, right? So this is a very simple task to do, and it is quite obvious from this slide as well. Fine. So now that we have put the solution, the guess solution, into the cylindrically symmetric paraxial approximation, Helmholtz equation with the paraxial approximation, we have come up with equation number 13. Now, if you carefully observe at this equation, you will realize there are two parts in this equation. The first part is dependent on r, whereas the second part is independent of r. And you know r is the transverse radius, right, of the snapshot of the beam, right? So if you cannot say it radius, rather it is a position vector on the transverse beam, right? The snapshot of the beam in the transverse direction. So if the sum of these two terms is equal to 0, then you can quite simply infer that the individual term is 0. So we force these individual terms to be 0 just to satisfy equation number 13. For that, we said that this whole term is 0, but since psi cannot be 0, this whole multiplication constant, or the factor, is not constant, rather this multiplication factor cannot be 0 as well, then the only possibility is that this term in the square bracket is 0. So if we assume this square bracket to be 0, and obviously the only possibility is to make it 0. So if we do this, we come up with this first order differential equation with independent variable z and dependent variable or the solution q of z. So next task is obvious. We need to find q of z. For that we need to integrate this equation, right? If we integrate this equation, differential equation, we come up with a solution which is q of z is equal to z plus some arbitrary constant. We assume this arbitrary constant to be q naught, right? So if we put this constant to be q naught, then the next task, this derivation basically tells us or basically compel us to get to know what q naught is, because this is just an arbitrary constant so far. So we need to figure out what is the precise meaning of this q naught is. Fine. So what we do next is we plug this q of z and we set the initial condition that at z is equal to 0, q of 0 is equal to q naught. And if you put this in the solution, the guess solution part, which contains this term, right? If we take the only this term from here, kr square over 2q of z, if we take this part, just for the moment, just to avoid complications, we took this part because this is q dependent. So if we take this part and put these conditions here, we get this thing. So here you have to put z equals 0. So q naught is equal to q of 0 is equal to q naught. If you plug this in, right, you suddenly realize that this part of the gas solution is very much similar to the Gaussian function, because we are dealing with the Gaussian beam and we expect that the transverse beam profile of the Gaussian beam is going to follow the Gaussian function. So that clearly guides us that this exponential term has to be real, because this is not a phase term. Gaussian functions do not possess the imaginary argument of exponential, rather real. So then the next thing that comes in our mind automatically, just to make sure that this is the Gaussian intensity profile exponential function, which is going to give us the transverse intensity profile, Gaussian intensity profile of the transverse beam, transverse part of the beam, which is going to get the transverse profile. So then we have to forcefully assume that q naught is imaginary. So let's call it q naught equals j. J is iota, j is the imaginary number, j is e naught, because this is the only possibility which will make this exponential, the argument of this exponential, to be a real number or a real valued, right? So from here we just realize that this arbitrary constant is not just an arbitrary constant, rather this is a specific imaginary number, right? So far we got this thing from here. So if this is the case, then what is the width of that Gaussian, right? So in order to find the width of this Gaussian, we take a standard Gaussian function to be of this form, and obviously where omega naught square is the variance which gives us the width of the Gaussian. So if we compare this part of the special profile, special envelope profile at z is equal to 0 with the Gaussian exponential, we realize that we can find the width of the Gaussian function omega naught in terms of these different parameters over here. So omega naught square turns out to be k r square over 2 q naught. By the way, r square should not be here. Right? And more precisely, q naught should be there, rather z naught should be there, because we just realized q naught is iota z naught. So we will do it later. So right now we just did what you have, what basically we have to do. So now we got q naught to be j z naught. So if you put this here, we get this thing, means exponential term, while putting q naught to be an imaginary number, j z naught. So now we have specified what this z naught is, but the interpretation is still yet to be explored. But so far so good. We will discuss it later in few minutes. So using this analysis, we find that the width of the Gaussian distribution, while comparing equation number 13, 17 and 18. So we have 18 and we have 17. So if we compare this denominator of this Gaussian exponential, which is the width of the Gaussian or the variance, with equation number 18, we realize that omega naught is equal to under the root 2z naught divided by k. So now the question is what this thing is. This is the beam waste. This is the minimum possible beam waste that a beam can get. Like if you pass a laser beam, let's say if you have a plane wave, crudely speaking, if you have a plane wave, let's say we are taking it from, let's say, some sort of laser, crudely speaking, then if you pass that laser into an optical element, such as, let's say we are passing it through the convex lens, then the convex lens is going to converge that beam up to a certain minimum beam waste. Beam waste is the minimum possible beam waste that it can get. So this is the lens. The beam has a certain diameter with a certain radius, but the moment it passes through the lens at a certain distance, which is a focal point, at the focal point it is going to get the minimum possible waste. Right? So here at z, we define this point to be z is equal to 0, and we define at z equal to 0, we define the radius of this transverse profile of the beam is the beam waste radius, right? So omega naught is the waste. Okay, so remember, from the wave theory of diffraction, we know that we cannot make a beam waste smaller than omega naught because of this Abbe's limit, diffraction limited optics, right? Abbe's limit was found in 1873 that light with a wavelength lambda traveling in a medium with refractive index n and converging to a spot with the half the angle, means if this is the optical axis, then this is the angle, right? So this is the angle that a beam will, with the minimum beam waste, will get, right? So Abbe found in 1873 that light with a wavelength lambda traveling in a medium with refractive index n converging to a spot with the half the angle, obviously the whole angle is theta, so this is going to be half, will have the minimum resolvable distance, means any optical element is going to make the beam waste to be 0. Rather, it will be finite. It will be minimum, or it will be of minimum possible width, which is restricted by this Abel's limit. This is a fundamental limit in optics, that you cannot make the distance more resolvable than this angle, minimum possible angle on the beam, right? So if we say the resolvable distance for the light which is coming through this lens is d, then you can see d is directly related with lambda. If you want to make the imaging precise or resolvable imaging, then you have to make your lambda as small as possible. Means instead of using red light, you have to use blue light. Instead of using blue light, you have to use UV light. Instead of using UV light, you have to use gamma rays. But in the end, still lambda will be finite, so d will be finite. Similarly, so n sine theta can be replaced by the numerical aperture of the lens. So now, in order to make d 0, means arbitrary precision in the resolving distance, or you can say minimum resolvable distance is 0. It will only be 0 if the aperture or the numerical aperture of the optical element, such as lens over here, will be infinity. Means you have to have infinitely large aperture. You have to have a convex lens with an infinitely large aperture just to make the precision as precise as possible, like with arbitrary precision. Because remember, I'm not using quantum mechanical idea, I'm just using classical optics, wave optics. I'm using the Abbe's limit. So since these two situations cannot be fulfilled, right? So we cannot expect to get the resolvable distance to be 0. There will be some finite distance, which is basically in nature restricted by lambda and numerical aperture. It has nothing to do with the inability of making precise measurement, right? It is a fundamental limit imposed by the diffraction theory in optics. So fine. So the minimum possible radius that a beam can get is called beam waste, which occurs at z equal to 0. Right? So now that we learned what is omega naught and z naught, so we can write z naught in terms of omega naught. And so you can see this is the formula for, so this term z naught is, in literature it is called confocal parameter. And it is very famous. It has another name which is called Rayleigh length. And what does it say? Rayleigh length says if the wavelength of the beam is larger, Rayleigh length will be smaller. Similarly, if the beam waist is larger, Rayleigh length will be larger. If the beam waist is smaller for a certain given wavelength lambda, then Rayleigh length will also be smaller, right? So this Rayleigh length is going to be a very important parameter, which I will be discussing in this lecture later, right? Because for that we need some figures. So the figures are in next pages. Yeah. So this is called Rayleigh length or the confocal parameter, where you can see this is the pi r square. This is the area of circle. So if the beam is like this, means here the beam has minimum spot size. So this is called omega naught. So the area of this region, the transverse section of this beam, is pi omega naught square. So if the area of beam, the area where if the area where the beam spot is there is smaller, Rayleigh length will be smaller for a given wavelength lambda, and vice versa. Right. So now we were in the quest for finding Q, and now we have understood what this Z naught is. Right. So now we realize that Q of Z is not just a real number, it is a complex number. Right. So if this is the case, then as you know, the Q of Z term in this equation, which is assumed solution here, you can see Q of Z appears in the denominator. So that is why we are going to take the reciprocal of this Q of Z here. And since the imaginary term is appearing in the denominator, so we rationalize this and find a multiplicative inverse of Q of Z as follows. 1 over Q of Z is equal to Z divided by Z square plus Z naught square minus J Z naught divided by Z square plus Z naught square. Right? So if we plug this equation number 22, into equation which is the solution, assumed solution here, we get this form, this thing. So P of Z is where it is, right? We have not disturbed this P of Z term. We have only been dealing with Q of Z term. So this is the thing. So now, if Z is greater than 0, means if you are moving away from the beam waist, then you can realize that this term has to have some meaning. This term has to have some meaning. This term, apart from this R square, this term. So initially, this was instead of this term we had Z naught term only. So we defined beam waist, and now here in the denominator Z is also appearing. So we can equivalently define the beam radius at any value of Z as follows. So if we compare this with exponential minus R square over omega of Z square, we realize that this term here is the beam radius, right, at any Z. So 1 over omega square Z is equal to this term apart from this R square. Remember, we don't need to discuss this thing right now, and we are not interested in interpreting this term because we are dealing with the real term here, and this is imaginary, and we will be discussing this term later. Yeah. So 1 over omega square Z is equal to, so this whole term is here. So if you simplify this term, it turns out to be this thing, which is equation number 25, that says beam radius at any value of Z, which is omega of Z, is equal to omega naught times the square root of 1 plus Z divided by Z naught whole square. Right? So as you can see, with the increase in the value of Z, omega Z is going to get bigger than omega naught. That means if you go away from the beam waist, you will always find that your beam is going to get bigger and bigger. Means the radius of beam goes on increasing when you are moving away from the beam waist, means from the Z equals to 0, right? So if you are moving away from Z equal to 0, whether on the right side or the left side, beam is always going to increase its radius. Size of the beam will start increasing, right? And it happens, right? So this is the thing. So therefore, we realize that Q of Z is a very important parameter, Q of Z, which has to do with Z and Z naught, and so whose real part gives us the information about the beam, which is this thing, means the radius of beam at any Z, whereas the imaginary terms gives us the information about the size of the beam or the beam waist at z equals 0, which is defined to be the origin of our beam. So what does this mean? It means that if somebody gives you this q of z number, complex number, and tells you locate the beam, then you can easily locate the beam using these two terms, z and z naught, or omega naught and omega of z. Why? Because z and z naught are connected with omega of z and omega naught respectively. So this q of z is a very important parameter which is going to specify the size of the beam at any value of z, whether the value of z is equal to 0 or less than is greater than 0, or it's less than 0, means you are moving towards right or moving towards left. Yeah, so now we need to do some further analysis. So for that we take equation number 25 and we assume what this z naught is. So far we have not decided the significance of z naught, right? So in order to understand how z naught scales the spot radius at any z, we set z is equal to z naught, z is equal to z naught, or z equals z naught in equation number 25. Then we can see this z naught cancels with z naught, and there is the term which is 1. 1 plus 1 is 2, and if we take the square root of 2, then it turns out to be roughly 1.3 omega naught. So what does this mean? This means that the value of beam radius at the z is equal to Rayleigh range, or the confocal parameter, is approximately equal to omega of z, or omega of naught. It means, yeah, I should better write omega of naught here. Means omega of z is roughly equal to omega naught if z is equal to z naught. Means within this Rayleigh range or confocal parameter, the beam is going to be roughly collimated. Means the beam will have roughly the plane wavefronts, flat wavefronts with infinite curvature, and the beam will have, since the beam will have flat curvature, or beam will have the maximum will have the collimated spot size roughly, then the beam will be intense within this region, right? And that has to do with the conservation of energy, right? So now we got to realize, we come to know that the beam is roughly collimated within this range, so with maximum intensity range. So that is why we call it confocal parameter. Means if you go z equals z naught, whether you are going towards left from z is equal to 0, from z is equal to 0 to the left, which is z is equal to z naught minus z naught, let's say, if we ignore the sign of the number z naught. Similarly, if you go right with respect to the origin, which is z equal to 0, again within this range, within these two focal points, within these 2 points, right, the beam is going to be roughly collimated and with a maximum intensity. So that is why this word is used here, confocal parameter, and it is also called Rayleigh range. So if you are interested in doing some kind of intense interaction with laser light or Gaussian beams in your experiment, then you have to place your specimen or the target material on which you are interested in shining this Gaussian beam will have the huge impact or the maximum impact within this range, right? So if we draw the diagram, so see here we have omega of z, and remember omega of z can have two values, positive and negative, because depending on the quadrant, right? Because we took the square root, so we can expect to get plus minus here. So if you see, if you plot z is equal to 0 here, you will be here. And if you plot z is equal to 0, then you will have the plus omega naught, which is here. And if you take the minus part, then you will be here. Similarly, if you go on increasing the value of z, then omega z is equal to plus omega naught times this term, which will say that your beam radius is going to increase. And obviously, if you go to the negative z-axis, again the same thing will happen. Similarly, if you take the negative part and start increasing the value of z, and since there is a square on z, so if you go negative towards negative z or positive z, then nothing happens. So you will have these two terms. Even if you do not define these things, this was just for simplicity, again you will have such kind of expanding behavior in your beam, right? This is the thing. So we will discuss these little parameters, what these angles are. So this is the confocal range or Rayleigh range, and so if the distance from here to here is z0, then the same distance on the left side is also z0. Within this range, you will see that your beam have minimum diverging or converging effect. So the beam will be roughly collimated in this region. So if you go away from z0, then you will observe that your beam is going to diverge drastically. It is no longer collimated, right? This is the thing. So now, yeah, so we did this thing. So if you apply some approximation and say limiting conditions, not approximation, that z is very greater than z, means you are far away from the confocal range, confocal Rayleigh range, then you can see, you can ignore, yeah, you can write it here. So if z is very greater than z0, then obviously this term will be very much greater than 1, so you can ignore 1. So if you ignore 1, you can cancel square root with the square, and you are left with this thing. So omega as a function of z will be equal to omega naught beam waist multiplied by z divided by confocal parameter z0. Right? So what we can achieve from this calculation is follows. So now that we have derived this thing, omega as a function of z, which is omega naught times z divided by z naught, right? So now you can estimate how omega is going to change with z. So in order to do that, you have to take the derivative here. So if you take the derivative, so this is going to give you the slope, means what does this omega d omega by dz means? With the increase in the value of z, how this omega increase changes, right? And since we are doing the paraxial approximation, we will say that this angle is not much larger, right? So this d omega by dz can be think of as this angle, right? So you can think of it like this thing. So if this is the z is equal to 0, and if you draw the parallel line here connecting z equals 0, then you can see as z changes, omega naught goes on increasing. So this angle is the diverging angle, right? So similarly here in the lower side, the same will happen here. Again, this is the diverging angle. So in short, these two thetas are basically the total diffraction angle. And how it can be proved? You can see it here. If you draw a line at z is equal to 0, a tangent, if you draw an asymptotic line over here, then you can see there is an angle which says that as you increase the value of z, the beam is going to diverge. So this theta is called theta d, diffraction angle. And for that, yeah, so since I took this thing from the book, so you can call it theta instead of theta. So this is theta d, which is 2 times the theta, or you can also derive it from here. So if this is the actual beam spot size, beam waist, right, and when it start diverging, it subtends some angle theta, right? So the same angle appears here. This is theta, this is theta, so the whole angle is theta d. From the geometry it's obvious. So d omega z by dt is d omega z by dz is theta, which turns out to be omega naught over z naught. So if we calculate the total diffraction angle, the diverging angle of the beam, which is theta d, which is 2 times the theta. So if you write this thing as this, theta d equals 2d, and plugging the value of theta here, right, you come up with this thing. And if, yeah, so if you cancel 1 omega from here, and if you write 1 over omega naught here, right, so yeah, I think, yeah, so there is lambda over there as well. Fine. So if you put the value of z naught, then lambda appears here. So now this is the diffraction angle. So this is a very interesting parameter, 2 lambda divided by pi omega naught. 2 lambda divided by pi omega naught. See, if the beam has smaller wavelength, then the divergence angle will be, diffraction angle will be smaller. And you can expect this, which is common with our common sense. So yeah, if you are using the energetic beam, this is not going to diverge easily or diffract easily, right? For smaller value of lambda, theta diffraction is going to be smaller. Similarly, if you have a beam with the minimum beam waist, it has got a tendency to diverge or diffract very fastly. So that is why theta d is directly related with lambda and theta d is inversely related with omega naught. So this thing is clearly identifying that this thing is right. So yeah, this thing is in agreement with our common sense. Yeah. So next thing. So now that we have specified Q, and from that we defined Q, Z and Z naught, and from Z and Z naught we defined beam waist, beam radius, and then we defined confocal parameter or Rayleigh range. And from the beam radius formula, we basically took the derivative with respect to Z, propagation axis direction, and we defined the diffraction angle. So far we have done half of the calculation because we defined Q, right? So the next thing is, we have defined Q, but there is another term which is appearing over here. When we were solving Q of Z, we get this additional term, and as I told you, I will be discussing this later. So the time has come to discuss this thing. And remember, these two terms are different because the first term is, as you can see, the first term has j iota in the exponential, so that has to do with the phase, whereas the second term is not a phase. So now is the time to discuss this phase, which appears in the derivation of Q of Z, right, in the solution of differential equation for Q of Z. So what does this thing is? What this thing is? Okay. So look. So if I isolate this term from here, then you can see this is a phase. Obviously, we can say this is a phase, but this phase is also depending on r square. Means apart from other things which we have decided what they are, but apart from those things, we see there is a j, a complex imaginary number with r square. So what does this thing is? The answer is, this r square is more like a parabolic function the phase is like a parabolic function. If we call this phase to be, let's say, chi, that is something times j times r square, then you can see, yeah, I should better call this thing, right, with something. See, chi varies with r square with j here. So this phase is more like a parabolic phase. So that is why this phase is called parabolic phase. And this phase has to do with z and r, right? So how will you describe this thing? See, this is a phase, right? And it has to do with r and z, and the phase is parabolic. So it gives us it. So in order to simplify this thing, we assume that the denominator, so there was a z in the numerator, so we bring that z in the denominator of the denominator and call this term r of z. Then this term simplifies to be in this form: e to the power minus j k r square 2 divided by 2 r of z. So now that r of z is defined in this way, then the next question is what this r is, right? So we should try some approximation or some assumptions here to understand what this really is. So let's say z goes to infinity. We are dealing this r of z in the boundaries, at the boundaries. So when r goes to 0, this equation says when z goes to infinity, means very far from the beam waist or even far from the confocal parameter, very far, r of infinity is infinity. That means it has something, it is something which goes infinity whenever the z approaches infinity. And similarly, even if z is equal to 0, means at the beam waist r of infinity is infinity. And you know, we call the beam to be a parallel plane beam, right, with maximum intensity, plane wavefronts at within confocal range or within Rayleigh range or within confocal parameters value. Then this thing simply says that this is some kind of curvature. And you know, the curvature of plane wave is infinity. So this r of z suggests that it is some kind of curvature which is infinite when z is equal to 0, and it is even also infinite whenever z is infinity, at infinity. Means this is a phase which comes from the curvature. Means the beam, as the beam will evolve, beam will start from the beam waist with the plane wavefront, and as it will move with this along the z-axis, due to this propagation, these plane wavefronts will start curving. So due to this curvature, an additional phase will come, right? Means it point source, let's say not point source, but here you can say omega naught z is equal to 0. The beam is plane, but as it moves, it is roughly plane, but when it goes infinity, it's flat. Here infinity curvature is infinity. Here curvature is infinity, but here curvature, but less than infinity. It's less than infinity, finite, right? So you can think of it this r of z as some kind of curvature which is due to the transformation of plane waves into some sort of spherical waves or partially spherical waves, and that curvature is going to give you an additional phase. which is also depicted here. So this is R of Z, right? Yeah. So now we have completely specified the functional form of Q of Z. As you know, one of R of Z is what? This thing, right? And Z naught is this thing. So we realize one over Q to be this thing. So half of the calculations are done because we have exactly specified and located what Q of Z is and what kind of information that it is giving us, and how we can specify the geometry of our location of beam waist and spot size anywhere on the optical axis Z, right, or the propagation axis. Yeah. So the next task is to solve the other half of the equation, which is the differential equation with respect to P of Z. Let me show you this thing. We solved this term and got to know so many parameters. And now is the time to discuss the second part. Again, k cannot be 0, psi cannot be 0 means that something which is appearing inside this bracket is 0. So how to deal with that? So yeah, we took this part of that differential equation, this, right, and try to solve this. So if we solve this equation, right, this is a complex differential equation, so I solved this by Mathematica. So you can even solve with Mathematica as well, because I didn't spend time in doing this calculation by hand to come up with the solution by hand. So this is a solution, right? This is the differential equation with complex numbers as well in this equation. So how to interpret this thing? So what is the value of P of Z? It turns out to be P of Z equals 1 over, sorry, P of Z equals log 1 minus Z over Z naught, right? And you can see the argument of log is a complex number, A minus iota B, similarly, right, of this form. So you can write it in the complex polar form. So the complex polar form says that you have to take the magnitude or absolute zero, absolute value of this number, which is this thing, and take the exponential with phase. And in phase you have to find the direction, which is theta equals tan inverse Z over Z naught. Here it is not theta, you can call it something eta, let's say, right? So this is the thing. So now we have solved this equation, and we have come up with this particular complex parameter, right? Apparently we assume that it is a parameter or the solution to that simplified version of the definition, simplified differential equation, first order. So this thing came in result, right, in return. So if we can simplify this further, because this is function A, this is function B, and there outside this A and B there is log, so log of A multiplied by B is log of A minus plus log of B. So if you take the log of B here, exponential and log are opposite to each other, so minus with the plus is minus. So this thing basically volatilizes to this simpler form. So if you plug this thing, put this value of P of Z and the value of Q, 1 over Q of Z in your exact solution, in your proposed solution, yeah, where is the solution? Yeah, here. So if you put the value of P of Z and Q of Z here from equation number 30, 33 and 29. So if we use 23, 29 and 33 and 23, which is our gas solution, we come up with this term, right? So if we further simplify, because there is exponential to the power minus log minus into something, so we can distribute exponential to these terms and cancel log with exponential, then this comes down in division because there is a minus out there, right? So similarly, if you take this term exponential of minus j, this remains here as it is. Similarly, there are two terms which appear, so if we distribute exponential terms, different terms, by separating to the exponential, we are left with this thing. So now that we have the amplitude function profile over here, so if we plug or put this thing in our actual solution, which is E as a function of x, y, z, right, where psi is equal to equation number 35, we get this thing, right? This is our result so far. Remember, E naught is the amplitude of plane wave at z is equal x is equal to y is equal to z is equal to 0, right? So this is the thing. So if you notice, the term in the denominator is very much linked with the beam spot size. So if we multiply with omega naught and divide with omega naught, we can transform this denominator in terms of omega of z. So see, E naught times omega naught divided by omega z appears here. Similarly, we bring out this Gaussian distribution, which has to do with the intensity, transverse intensity. We bring this in front of this omega z term, this omega naught over omega z term, then we realize that these terms are very nice looking arrangement, right? So these has to do with the amplitude, and so omega naught omega z has to do, since the omega z is in denominator, then what is this going to do? This is going to decrease the intensity with the increase in the value of z, and when you bring z closer to 0, it will increase the spot size up till until it gets to z equal to 0, where the beam waste resides, where the beam waste is. Fine. Similarly, so now it's the time to discuss this term, which is this thing. So you can realize that e to the power minus j is a complex number times something, is indicating us or giving us the smell that this has to be some kind of phase, right? So this is the phase. Similarly, this another term is also the phase which comes from the curvature, as I discussed earlier. Similarly, yeah, this thing is redundant, so don't consider this. And the last term is also called the longitudinal phase term due to the propagation of beam along optical axis z, right? So now let's discuss this term, right? This is the only relevant phase term which is not yet discussed. So what this thing is, right? So this is an additional phase. This is also called Gauss phase, right? Which has to do with the phase velocity, which I will be discussing someday. It is a different topic in detail. Obviously, it requires a rigorous mathematical treatment. So, but yeah, you can mathematically assume, mathematically understand what it is. See, let's say the beam is coming from minus infinity, then z is equal to minus infinity. So the value of this phase at minus infinity is 10 to the power minus infinity divided by z naught. And you know the value of phi turns out to be 10 inverse minus infinity. So 10 inverse minus infinity is minus pi by 2. Similarly, if you move from z is equal to minus infinity all the way to z equals plus infinity, there appears an additional phase which is plus pi by 2 at z is equal to plus infinity. So if you find the phase change in propagation from z equals minus infinity to plus infinity, your electric field profile gets an additional phase of pi by 2 plus pi by 2, that is pi. This is called Gauss phase. this thing I have already derived here. So for example, beam comes from z equals minus infinity to z equals plus infinity. So the total phase change is, just to avoid this minus sign, I took the absolute value. The absolute value of this change in phase in propagation from minus infinity to plus infinity along z-axis, this turns out to be tan inverse minus infinity by z naught minus tan inverse infinity by z naught. So minus tan, as you know, tan is odd function. So minus comes out in front of this tan inverse function. So tan inverse infinity, similarly this is tan inverse infinity. So minus pi by 2 is minus pi, and if you take absolute value, this turns out to be pi. So due to Gauss phase, this beam, when propagating from minus infinity to plus infinity, gets an additional phase of pi. But yes, if you are not interested in saying the beam is coming from minus infinity, rather you say I'm discussing my problem while assuming my beam waist to be at origin, means beam waist is origin, and the beam is going towards plus infinity, then there will only be a Gauss phase of around pi by 2 radian, right? So this is the Gauss phase. So now that we have the complete solution of this Gaussian beam, which is derived from the Paraxial Approximation in Helmholtz Equation, while treating our beam to be cylindrically symmetric, or you can say while using cylindrical coordinate system, we get this solution, which is equation number 38, right? Apart from this is redundant, this thing, where this is the phase. So this is electric field. So if you take the complex conjugate of this electric field, this becomes positive, and positive. So we have E electric field and complex conjugate electric field E star. And if we find intensity using this formula, normalized intensity, or you can simply say intensity, if you do not divide E naught by E, then this is intensity, right? If you divide it, then it is called normalized intensity. So the normalized intensity is E divided by E naught mod square, which is E star E divided by E naught. And so if we multiply E star with E, then phases disappear to 1, means phases cancel each other, and E to the power 0 is 1, and we are only left with those terms which do not have an imaginary number, right? So, and that is going to give us the intensity of the beam. The beam, all the phases are appearing along due to the propagation along z direction. So all those phases are cancelled. So the intensity which is left is along x and y axis, right? Because electric field is there. So you get the intensity profile of the beam to be Gaussian function. And the amplitude of intensity, or the intensity, is basically attenuated as 1 over omega of z.